So the goal today is to present to you a proof that the uniform infinite planar triangulation is recurrent, or that any local limit of planar graphs that does not necessarily have bounded degrees, but that you know something about the statistics of high degree graphs. So if you have a sequence of finite graphs, planar, such that the amount, the fraction of vertices of a degree at least k is exponentially small in k, then you can infer that the local limit is recurrent. And I'll just tell you that indeed this exponential decay is tight. And if you have anything that is worse than that, then there is a counterexample. And in exercise sheet 3, you can see why, or an example in this vein, one of the exercises there is to construct a transient example of such a limit, such that it possesses any finite moment of the degree. So finite moment is not enough, but an exponential moment is what you need. And the problem is, of course, that we can still circle pack this graph. There's no problem, and we even know some things about the circle packing of it, but we are unable to deduce, without bound on the degree, we are unable to deduce from the drawing any relevant information about the resistance. So in fact, we will not circle pack this graph. We will make a reduction to the bounded degree case and only circle pack a bounded degree graph. So let me start by presenting to you the reduction. This is the main tool that you need to prove this. This is on page 59 of your notes. We called it the Starfree transform. And it is really an ad hoc trick. It's nothing that is systematic to deal with this precise problem, and probably it has no usage to anything else in the world. So you start with your planar graph that may have unbounded degree. So let me describe to you the transform just in a drawing, and you can read the precise description. So I start with, let's say, I have a vertex of degree 6, right? And I assume that I'm in the world of triangulations, right? Because I can always reduce my graphs to triangulations, and it only makes my life worse. So if I prove the triangulations and the limit are recurrent, then I get that any limit of planar graphs. So I have this graph, right? And the degree is very large. It's 6 here, and perhaps some other vertices here. Okay, so let's just stop with this, because it's already going to be a difficult drawing. So the first thing that I do in the first step, and you can see the picture on page 60, I'm going to put a vertex in the middle of each edge. Let's right. And now I look at each original vertex of the graph. I have a vertex that is white in this drawing. And instead, as you see, what comes out of it is a star, right? It's just right, in this case, 6 edges going to 6 different vertices without any other edges. And this star I'm going to replace with a binary tree that is as balanced as I can. Okay, so if this vertex, let's call this vertex V, right? Then I'm going to transform it to this vertex V. Now I'm going to draw a binary tree that has 6 leaves at the bottom. Okay, and I'm doing it as balanced as I can. Of course, 6 is not a power of 2, so it's not going to be perfectly balanced, right? But it's going to be 1, 2, 1, 2. And now I have 6 leaves, right? And these are the vertices corresponding to the endpoints of the star, right? So I did this, and I do this to every. Oh, I forgot to put the middle edges here. Right. I put the middle vertices on each of the edges, and then now for each original vertex I draw the corresponding tree. And then I glue them together so that everything fits in a planar way. So if this was V and this is U, right, now U has 4 children. Right, I'm going to write it as a binary tree of height 4. Right, so here I will have U. Right, and U is attached exactly to, right, it has one vertex that is that corresponds to that is a neighbor of V. Right, let's say let's give them names. Right, 1, 2, 3, 4, 5, 6. And U has U's neighbors are 1, A, B, C. Right, so 1 is a vertex I've already drawn. So I will draw U this way. Let's say this will be here, here. Right. Or let's do it here. Now it has 2 vertices. Okay, perhaps I should have worked on this drawing better. So now U is a tree of height 2 that has 4 edges, right? And this I will attach, if this was 1, right, I will attach this edge to here. Right, so this was U, and these are A, B, C. I maintain the order of the I maintain the order of these leaves. Right, so this was 1. This is A. This is B. This is C. Right, and now when I have a vertex here that corresponds to 2, 2, 3, 4, 5, 6. I'm going to draw it here and attach the edge to 2. Right, and this one I'm going to draw here, etc., etc. So what you think about is each vertex you replace with a tree, right? And then you can glue the leaves exactly, right? Each vertex here, I could just erase these edges and draw a tree. Perhaps this would be a better drawing. Right, now this vertex has these edges, and this vertex has these, these edges, right? Each star I replace with a tree. It's kind of hard to draw, right? But it's clear that I can maintain planarity when I'm doing all these gluings, right? That is the only important thing, right? So here I have, perhaps I'll do something like this, right? And then something like this. And then these two will be connected to here. This will be connected to here. This will be connected. Okay. Perhaps I made too many edges. Something like this. And I continue doing this on all the graph. Okay, so every original vertex I replace with a tree, and I put it in exactly so that everything fits snugly in. This picture turned out to be weird, but it is clear that you can do such a thing. What is the maximum degree of the transformed graph? 3, right? No matter what you started with, each vertex, the original vertex, you'll have degree 2, and each of the inside vertices you will have degree 3, and each of these leaves will have one more vertex touching them at the worst case, right? So the degree of the leaves will be 2. So the maximum degree of this graph is at most 3. Okay, so if I start with any finite or infinite planar graph without any bound on the degree, this is the transform that turns it into a bounded degree graph. A maximum degree 3. And when I look at it, of course, this graph, if I started with something, of course, the new graph is going to be more recurrent, right? I took, for instance, I took a vertex, right? The distance previously between V to the vertex 1, I had one edge between them, and now I have, perhaps a long path between them. So I have the feeling that the resistance have grown, right? So it is somewhat clear that if the original graph was recurrent, then this graph will have to be recurrent. And you can prove that, but this is not the direction that we want to show. We want to show that if this graph is recurrent, then this graph had to be recurrent. But this is also not true, because here the resistances have really grown. So the true statement is you take this graph, and if you decrease the edge resistances on it, so you put weights on the edges, resistances that are smaller, right? So and you assume that the graph is recurrent, then the original graph had to be recurrent. So this bounds you. So this new graph, the transform, is indeed more recurrent, but this tells you by how much it became more recurrent. And this is the main idea of the proof. So let's state the lemma. Right, so the transform was, just my notation is going to be, if G is the original graph, I transformed it into G star. Right, and the important thing perhaps to notice at this point is that this is a local change in your graph. So in order to determine how the neighborhood in the, how is the ball in graph distance of distance 10 in your new graph, you just have to look at the ball of distance 10 in your original graph. Right? So this is, I don't have to look very far in the graph to determine how does the transform look like. I'm just doing these operations and that are local, or if you want a formal statement, these operations are continuous in the space of that we call G bullet or M bullet, right? The space of rooted maps. So the important lemma is the following. So I have G transformed into G star. Right, so, and G is an infinite or finite planar map. It doesn't matter. Set edge resistances on G star by putting R of E, so the resistance on an edge at G star is going to be 1 over the degree of V, where degree of V is the degree of V in the original graph, and you set it for every edge that belongs to the tree of V. Degree of V is the degree in G of the vertex V to which E belongs to its tree. In G star. Right, so for instance, if in the original graph the degree of the vertex inside that is now erased was 6, then the edge weights that I put on all of the edges corresponding to this tree is going to be 1 over 6. All of them. Right, so I put edge weights, and I put this is the recipe to put edge weights on all of the transformed graph G star. Okay, then the statement is if G star is recurrent, then G star with the weights RE. Right, so not just the graph itself, but when your random walker walks with the conductances, which are the inverse of these resistances, as usual. Right, so I definitely decreased the resistances on this graph. Right, so this is the and still when I do that, if it is recurrent, it implies that the original graph that is more transient is also recurrent. So it works in the right way that we want, and G is recurrent itself. Okay. And of course, we will apply it when G is the UIPT, and G hat will be this transformation. So our goal after we prove this will be to prove that with these new weights, the bounded degree graph is recurrent. Okay, and this is why we. So let's first prove this lemma and see proof. So the proof is kind of drawn on page 61. So just to remind you, if I had a vertex of degree 6, so let's start with let theta be. So let's assume by contradiction. No, let's assume that let's prove the converse. So let's assume that G is transient and prove that G star with these weights are transient. So assume G is transient. And let theta be the unit current flow from some vertex, I don't care which it is, right? From some vertex from A to infinity. So A is some vertex. And this unit current flow, because the graph is transient, has finite energy. So the energy of theta, right? The sum over the sum of squares of the values of the flow on each edge, this is finite. Right? This is our assumption, and our goal will now be to construct a new flow, or to construct a flow on G star that also has finite energy and has unit strength. Right? This will prove. So we will build flow, let's call it theta star on G star, such that the energy of theta star, and now the energy, I'm taking it, if G, the edge resistances were just one, were just unit, here I'm looking at the energy of theta star with respect to these resistances, right? So it's not just the sum over the edges of the square of theta star, but for each edge I multiply the square by the resistance, right? And this is the new energy. This is what we proved. So that the energy with respect to the edge weights RE is also finite. How am I going to do this? Let me tell you first what is theta star, and then we'll prove that its energy is finite. So I had a situation like this, right? This is in my original graph. I have a vertex V, right? And I have 6 edges coming out of it, right? And let's look at the values that theta writes on this edges, right? So theta is a flow, is a current flow that we are given, right? So it has values theta 1, theta 2, theta 3, theta 4, theta 5, theta 6, right? And in my transformed graph, right? It looks this was V. My transformed graph G star looks like this. Right, V is this. Right. One, 2, 3, 4, 5, 6. Okay, and I need to tell you what are the values of theta star that I put on each of these edges. So I'll tell you what they are, and it will be clear how to do it for a general when the degree is general and not just 6. So at this edge, right, this is the edge leading to the vertex 1. 1, 2, 3, 4, 5, 6. I put the value theta 1. So the directions are important, right? So right, because it's an antisymmetric function, so if the flow goes this way, I'll put it this way. All right, and here I'll put theta 2. And on 3 at the edge leading to the leaf, I'm putting the original values of the flow theta. So this will be theta 3, theta 4, theta 5, theta 6, right? And then when I have this edge that is the parent of these two edges, right, I have to put there theta 1 plus theta 2 going in this direction. So I'm putting here theta 1 plus theta 2 on this edge. Right here I'll put theta 3 plus theta 4, right? And these edges I've already put in the values, and everything, the direction goes down, right? So it's the same direction as here. And on this edge I will put the value, right? I'm looking at all of for each of these trees, I'm looking at all the leaves that are my ancestors, and I'm adding the values of this flow, right? So here, on this edge that just touches the vertex V, I will write theta 1 plus theta 2 plus theta 3 plus theta 4. And on this edge, it will be theta 5 plus theta 6. So notice that once I put the values, right, and these will be the values of theta star. Okay? Once I put the values on the leaves, on the edges touching the leaves, everything is determined, right? Because theta star has to be a flow. So the mass going into a vertex has to be the mass coming out. And you can see it here. At this vertex, I have mass entering, which is theta 1 plus theta 2, and exiting on this edge theta 1, and on this edge theta 2, right? And so forth. right? So this is indeed a flow. And notice that it's indeed a unit flow with strength 1. So if V is a vertex that is not A, right, then the sum of these will be 0, because the sum of these is 0. And if it is A, then the sum of these is 1, and here you have the sum of these is 1. So this will be exactly a unit flow. It is not necessarily a current flow. We don't know that. But we have constructed a flow, and now all we have to verify is that this flow has finite energy, right? And the fact that our resistances are smaller than what we wanted guarantees that this flow will be of finite energy. So is the construction of theta star? So this is theta star. Is the construction clear? Right, it should be, and it's depicted in this beautiful drawing at page 61, which of course not I actually drew it because I cannot. And in general, it should be clear that if I have here a larger degree, this works, for any, this construction is well defined. So let's try and bound the the energy of this flow. Okay, so now imagine, so this is the drawing, but in general we have a vertex V, and the tree may look much deeper, right? So right, and the number of leaves, right, is exactly the degree of the original vertex, right? So the number of leaves is actually going to be exactly 1 over the edge resistance and that I'm putting on all of these weights, right? So we want to estimate the energy of theta. So let us first estimate. Let's say I have here. Let's say I have here an edge, right? This edge here, right? And let's say it is of height L, right? So it's of height L from the vertices. So it has below it 2 to the power L vertices, right? And the values on these edges is right. So if here I had theta 1, theta 2, theta 3, theta 4 up to theta 2L. Right, the value here is theta is the sum of all these numbers. Right, so let us compute. Right, for this particular edge E, let us compute its contribution to the energy of theta star. Right, so we're writing its resistance times theta star of the edge E. Right, so this is exactly right the degree of V. Right, so I will have here 1 over the degree of V. Right, plus, and here I have to square, right? I'm computing the energy, right? I'm estimating the energy. I'll have 1 over the degree of V. Perhaps I'll continue here. Right, so RE times theta star E square equals 1 over the degree of V, right, times the sum of all of these leaves that are under all of these leaves that are under the edge, right? All of its children. So let's call it V that are children of E. Okay, and I'm summing their original theta, right? So this will be, let's call it theta V. Right, so I'm theta V is just if in the original graph I had this vertex V. Okay, I had this vertex U. Right. So let's not use the letter V because I already have V to be the root of this tree. So I have U. So if this was V and if this is V and this is U, I called this to be theta U. So it's exactly what I called previously theta 1, theta 2 up to theta 6. So I'll have this square. Okay. So now the only trick to this proof is to apply Cauchy-Schwarz in the right location, and this is the right place to apply it. Cauchy-Schwarz, or Schwarz inequality, as you call it. I don't know. Let's not get into this political matter. I have 1 over the degree of V. The number of things that I'm summing here is 2 to the L. Right? These is the number of vertices. Right? This is theta V times 1. Right, the sum of AI times BI is smaller than the square, is smaller than the sum of AI square times the sum of BI square. Right? Who remembers it without writing it to himself? So this will be 2 to the L, right, times the sum of theta V square. Right, when theta U square, when U is a child of E. Right, and E is an edge at height L. Okay, does everyone agree with this calculation? So now my goal is to sum this estimate over all the edges, and I'm going to do it in two ways. So firstly, so height L, if I had here 2 to the L, that means that this is the height. Right? So it's height from the leaves, right? Not the height from the top of the tree. So firstly, I'm going to sum over all the edges that are at height L. How many of these do I have? Right, so if this entire tree is of height h, right, h is exactly log, or approximately log of base 2 of the degree of v. Sorry, so how many edges do I have here? 2 to the power, so this is h minus L. Right, so I have 2 to the h minus L such edges. And when I apply this estimate for each of the e's at level L, right, I'm summing here, what I'm summing here is exactly a disjoint set of children, right? Each edge at level L, its children are disjoint, and their union are all the leaves of the tree. Right, so if I sum this estimate over all E at level L, what I get is of this term, of the resistance times theta star E, I get here 1 over this is smaller than 1 over the degree of V. Let's call it just d of V. 2 to the L stays. And then I'm summing over all of the theta U for any U that is a leaf. Right? Theta U square. Right? And this is exactly, right? This expression is exactly the sum of squares of all the edges of the flow theta of all the edges coming from the original vertex in the original graph. Did I make a mistake? Why?
There are 2 to the h minus L there.
Yes, but I took this estimate and summed it over all the edges E. Right? For each E, I get here another term. Right? A different term. Right? So I actually did not use the fact that they're numbers 2 to the h minus. So everyone agrees with this? So now I summed each level. I summed, right? And I want to sum over all the levels. Right now. So if I look at the sum over all the edges E, such that E belongs to the tree of V in G star, of R E theta star square E, I'm essentially summing this estimate, right, over L from 1 to h, where h is log to the base 2 of the degree of V. Right, but this is exactly the same thing, right? So this now, and the sum over 2 to the L, right, exactly from L from 1 to h, only this is a geometric sum, so the last term is the one that counts, which is 2 to the h, and that is exactly up to a constant, the order of the degree. So you could check that this constant turns out to be 4 or 2 or something like that. So this is smaller than, let's say, 4 to be safe. Then the sum over all the u's that are a leaf in tree of V of theta u square. Right? And this is it, right? So this is just the sum of squares of all of these things with no resistances. So when I sum, so the energy of theta star with respect to RE is no more than 4 times the energy of theta in G, right? So this is in G star. and this is in G. So if this was finite, then this is finite. Any questions about this? Right, so this is fairly simple. And lucky for us, the rest of the proof is now also fairly simple. And we just have to gather everything together. So let's proceed to the proof of the UIPT. The UIPT is recurrent, but before we do that, I want to state just one estimate from electric networks that I will use that I didn't prove to you, and I apologize for that. It is a statement at page 17 of your networks, and if you don't know it, it's worth knowing. Also, you could take it as a difficult exercise, even though the proof is written right there. So who will be the one that is not tempted? So we have this. So this is just one more ingredient that I will use in the proof. So let me just quote it to you. And if we'll have time at the end, I will prove it to you. So this is called the commute time identity. Right, and this is a very nice thing that states that if you have a network, or just a simple graph, right, and you have 2 points, right, the source and sink, and you're looking at the time, and you start a random walk. You start a random walk starting at A, and you look at the time it takes you to get to Z, and then come back to A. Right? So perhaps you visited A many times, but that's fine. You're still counting the time until you visit Z, and then you're going back to A. Right? So and it turns out that there is a precise formula for this expected time in terms of the effective resistance between A and Z. So this time is actually proportional to the effective resistance, and I'll tell you what the constant is. And in fact, this formula could be taken as a definition of the effective resistance, and all the conclusions that we know about it can be established from this. So the formula is the expected time when you start from A to reach Z, plus after you reach Z, the expected time it takes you to go back to A, right? This is the hitting time of the vertex A, equals twice the effective resistance from A to Z times the sum over all the edges, see the conductance on the edge. All right, and this is a very nice, very, very useful estimate about random walks. If you don't know it, I very, very much recommend knowing it, remembering it, and every time you have a question, try to use it. So for instance, if your graph is a path of length n, then indeed, at least, the time it takes you to get from here to here and back, right, should be, if this is n, should be of order n square. Right? So let's just not worry about the exact constant. And indeed, the resistance is from here to here is n, right? And the number of edges, right, each one receives conductance 1, is 1. So you get n, so you get n square here, and it even gives you the right constant, right? So right, with 2, so you know, in fact, that this is a completely symmetric thing. These two things are equal. By the way, in general, are these two things equal? No? No, they're not, right? What is an example?
Get the line from A to Z, and then from Z to...
Right. So for instance, if this is Z, you have one edge to A, and here you have a giant graph that is even complete, for instance, right? The complete graph on n vertices. So the time it takes you to get from Z to A is 1, deterministically. But from A, right, it's going to take you a long time to get to Z, right? Because you're going to be sucked into the complete graph. You're going to have to wait until you return to A n times. And only each time you're at A, you have probability 1 over n of returning. So indeed, the amount of time is of order n square. Right, so the formula without the constant still holds, right? Because the resistance is 1, but the number of edges, right, is n square. Okay, let's look at another example that may be interesting. Is the binary tree, right, of height h, or height n, right, you have the binary tree, and I'm looking at z to be the union of all the vertices at height n. Then the resistance from what is the order of the resistance from the bottom to the set of all leaves? Sorry, it's a constant, right? And the number of leaves is exponential in the height, right? 2 to the n. And what is the amount of time it takes to get from here to here? Sorry? It's height. No, just the height, right? No square, because you have a drift upwards, right? Each time you're here, you have probability 2/3 of going up, 1/3 of going down. So it actually takes you a very short time, which is the height, to get to the leaves. But the commute time is of order constant times the size of the graph, which is exponential in the height. And indeed, the first part of the commute, right? You're getting from here to here, from the bottom to the leaves, is going to be very fast, right? Linear in the height. But then to get down, that is the thing that takes you the majority of the time. It takes you exponential time to get back to here. And the only thing that we will be using, the only estimate that we will need is that if you have, the only thing that we will use with respect to the commute time identity is the corollary. If G is connected, right, and has n vertices, then for any a z, the expected time to reach z from A is polynomial in n. Connected, has n vertices, it's only polynomial. Right, and this is simply because if a graph has at most n vertices, the distance, and it's connected, the distance between A and Z cannot be more than n. Right, so the resistance is no more than the number of vertices. This is always true and is extremal in the case of a path. And the number of edges is also polynomial, right? At most, so perhaps a simple graph. So we get here a polynomial, right? This is all we care. We're not going to care if it's n square, n cube, n to the fourth, or whatever we want. All right. Any questions about the statement? The proof is on page 18 of your notes. It's not very difficult, and it's a classical thing. And now, are there any questions? So now I'm ready to explain to you the idea of the proof, given that we know the things that we know, and I won't be surprised if for some of you it will be, that's right, that's true, everything works. No need to listen to the rest of me blabbering, and that's fine. So what is the idea? Okay, perhaps before the idea, let's address one more point that I will not treat exactly and precisely, but you can convince yourself that it's a technical and not a very interesting point. In the notes, it's treated with great care, and that's why there's like perhaps an extra page or two in this note. And the issue, the slight issue, is the choice. So I'm reminding you, our goal is to prove we have a sequence Gn converging in the local limit to u rho. And what we know is that so how do we obtain this limit? We take, so what this means is that the ball of radius, ball around in Gn, around a uniformly chosen vertex, right, of radius r, converges in distribution to the ball in U around the vertex rho with radius r. And what is going to happen in this proof a lot is that I'm going to change the distribution of rho n. So the first thing I'm going to do is I'm not going to prove to you the theorem with this limit when rho n is a uniform random vertex of Gn, but rather when rho n is a stationary vertex of Gn. So instead of choosing it uniformly, so rho n is now stationary, the probability now that rho n equals v is going to be the degree of v, right, divided by the sum of the degrees by the sum of the degrees in Gn. So you may ask, the first thing that you may ask, but this is not what you promised us. Why do you lie? But the truth is that you can convince yourself that because you have a first and second moment on the degrees, then so I may get here a different limit, right? If I choose the root to be uniform or stationary, the limit may be different. But the statement that I'm not going to prove to you because it's fairly straightforward and not very interesting is that so the two limits, the two local limits may differ, but they are mutually absolutely continuous with respect to each other, or mutually absolutely continuous with respect to each other. So if I manage to prove an almost sure property, such as the property that the limit when you take this random root, you get an almost sure recurrent graph, will also hold for the original limit. And I'm going to do these kind of these small changes on the distribution of the root all the time. So sometimes I will choose a uniform vertex, and sometimes the probability of choosing each vertex will be perhaps not 1 over the number of vertices, but some number between 2 and 3, or between 3 and minus third, between 3 and 1/3 over the number of vertices. So even if I change the distribution a little bit, but it's still spread out, then the resulting limits are always going to be absolutely continuous with respect to each other. So, and the reason, or the underlying reason that why all of these things works is let me just write to you the fact, and you can translate this fact into why all I'm saying, why this statement is true. And the reason is if you have so this is a fact, that if you are not aware of this fact, then it will be very worthy. You don't have to prove it. You can, smoke a cigarette and think about it, and you'll see why this is true. If I have two measures, mu, probability measures on a finite set, 1 to n, right? And all you know is that a mu of x, right, is between mu of x and nu of x. Both of them are between some big constant over n and bigger than some small constant over n. Then there is a coupling between these two measures. I can draw two random variables on the same probability space between these two measures so that they are equal with positive probability. Okay, so there exists a coupling, right? xy, two random variables distributed xy, x is distributed according to nu, y is distributed according to mu on some joint probability space such that the probability that x equals y is at least some other constant. Right, so this tells you that if in one model I'm choosing the random root in some particular way, right, but such that this holds, every vertex has probability something like 1 over n, but not exactly. And then the other one, perhaps I'm choosing it precisely uniform, then I have positive probability that I've chosen the same thing. And this tells you that if in one of the models I had some event with probability 0, now it will have probability that is at most c times 0, right? Or at least that, right? And this gives you absolute continuity. So this is just this basic abstract measure theory that I don't want to get into. So from now on, we're going to assume, even though I'm going to choose roots in all sorts of weird fashions, I'm always going to assume that the root that even though it's not true, we're just going to assume that the root is a stationary vertex, chosen according proportional to the degree, in all of the graphs that we're about to see in what I'm going to show you. What is the advantage of choosing a stationary vertex? Well, it's just the word stationary, right? So why stationary vertex? It makes sense because we want to study the random walk on the limit, right? So and when I choose a stationary vertex and I make one step, my distribution is still the same as it was before. So if rho n is stationary, right, stationary vertex of Gn, right, and x1 is a uniform neighbor of rho n. Right, then when I look at the random variable, I have a fixed r. I look at the random variable b, g, n, rho n, r. Right, this is a random variable in our space G bullet or M bullet. Right, then this random variable has the same distribution as B, G, and X1 R. Right? Right? Simply because conditioned on the graph, rho n and x1 have the same distribution, and this is the only thing that matters here, right? The distribution of the random root. And this property passes to the limit, right? If I take limits on both sides, I will get that the ball of radius, as long as I chose rho n this way, the ball in U, right, around rho in radius r equals in distribution to the ball of radius r around a random neighbor of rho of radius r. Right, and this is true for all r. So what we get is just that the distribution. So as long as we chose our initial vertex to be a stationary vertex, we get that the distribution, right, as a full, right, the distribution of this random variable on the same space on G rho with the same topology that we defined has the same distribution as the following random variable. I condition on U rho, choose a random vertex of rho, and look at the graph rooted at that random vertex, then what I see has the same distribution. Right? This is the distribution U x1, and of course this is true for any number of steps of the random walk that I do. So this is what I'm telling you here is sometimes in the statistical physics literature is called the random walk from the point of view of the particle. Right? This is the particle, and and this is, where the location determines where I'm rooting, and I'm looking at my vicinity from the point of view when the root is the random walk. Okay. So the only point here, and so let's see what is the strategy of the proof. It is the following. Okay. So now let's write the plan of the proof. Plan of the proof. Well, it's a plan, but you can make this a plan. There's no further tricks that are needed, right? So we start with Gn, right? Rho n. Rho n is the stationary vertex, and this converges, right, to U rho. Okay, and now we're going to apply the star tree transform on this graph. So here there's a deterministic operation that makes this graph. Now this graph only has exponential tail on the degree, and I'm turning it into a graph that is 3 regular. So here I will have G n star, and I will choose rho n star. For instance, I could choose this rho n star to be the root of this of the tree. Right? Here I have a general planar graph with a particular vertex chosen. This vertex is turned into a tree, and I can think of rho n star as the root of this tree. Okay, so now you can see why I'm lying. This rho n star is not a stationary vertex of this graph, but let's pretend that it is for the sake of clarity. Okay, so in honesty, I will have to change this selection of the root on the transformed graph. But everything works, and I don't want to get into this detail. You can read it in the lecture notes. So I've transformed the finite graph into by the star tree transform, and then you can convince yourself that this will also converge. Just because it's a continuous operation, this will converge to something that I call U star rho star, And you can also convince yourself very easily, because of continuity, that this limit is the same thing as taking this graph and performing the infinite graph and performing the star tree operation on it, right, and obtaining u star, and choosing the random vertex, the root here, in the same way. So this is a commutative diagram. To create this object, I can go this way, or I can take the limit first and then transform it, and it gives you the same thing. Right? And my assumption that both rho and rho star, they are stationary vertices with respect to this. Right? So now I want to use the star tree lemma. Right? So the star tree lemma. So I have to prove that this graph is recurrent, but not with respect to the simple random walk. Why is it recurrent with respect to the simple random walk, by the way? Yes, you are right if you're mumbling. It's not a trick question. Sorry? It's bounded degree, right? This is the local limit of planar graphs that have degree at most 3. So we've already proved that this graph is recurrent with respect to the simple random walk. And in fact, we proved the quantitative statement. So the first thing, but before we deal with that, so we need to prove that it's recurrent with respect to the original weights. And if you remember, when I was telling you about the spaces G star, G bullet, and M bullet, I also said we want not just perhaps to remember the graph structure, but perhaps we also want to remember certain labels, certain numbers that we put on the edges. We want to remember extra information. Right? So here, we also want to, so here we have transformed the graph, but we want to remember, now we have a graph that is a collection of trees pasted together, but we want to remember the original degrees that we got from there, right? Which is essentially the size of the tree. So here I will not only remember the structure of the new graph, but I will also put here the new resistances that I defined. RE, right? And perhaps there's an N here. Right, and this RE, just to remind you, was 1 over the degree of V when V is the tree that E belongs to, right? And V is the original vertex here. Right, so we have this information, and I also want to make sure that it passes through the limit. So this is, again, just some sort of abstract nonsense, that it does pass through the limit, because all of these edge weights are determined locally by the information here. So everything that you can look locally, any kind of thing any random variable, any number that you can compute just by looking locally at your original graph. And here, you simply need to look at distance 1, right? You just need to count your neighbors, and you know exactly what number to put. So this also is maintained in the limit. So here we will get some edge weights that we remember from the limit. And our goal is to prove that this graph with these resistances is recurrent. Right? And if we know this, the lemma that we proved in the beginning of the class will imply that this is recurrent and that this is what we want. All right? So this sounds convincing. So now we have to ask ourselves, and this is the main point, why is this thing recurrent? So what is the sketch, and why is this thing recurrent? So we have let's in U star, rho star, RE. So let's define for each vertex of U star. Let's just write this number. MV is going to be the maximum over all the edges such that V belongs to the edge of this resistance. Right? So we have not used yet the fact that the degree has an exponential tail. But if you remember, these resistances comes from these degrees. Right? I guess all of them are smaller than 1. Then what I meant here was the conductance. Yes, 1 over this. Right. So what we know is that the probability. So I took the maximum of an exponential of exponentials, but this still has an exponential distribution. So we know that the probability in U star rho star that the degree that you came from, right, you can think about this as the degree of the tree, right, that rho has turned into. Right, the original rho has turned into a certain tree, and this m is the degree of that tree. Right? So we know that the probability that this is bigger than k is exponential in k. Right? So this is our assumption. Right? And we also know, because of stationarity, that this thing will be true. Right? This is the same number if we write here m of xk, where xk is the simple random walk on this graph. Oh, okay, bad note. xn, right, is smaller than c e to the minus ck. Right, so if I run the random walk n steps, right, I will not see degrees that are bigger than log n. Right, this is the statement, and here is where I'm using the stationarity. So this assumption of the degree that I'm seeing is not just true for the first vertex, but for the next vertex and third vertex of the simple random walk. So what did we prove about this graph? We proved that it was recurrent, but we also had a quantitative statement, right? I'm reminding you the quantitative statement. Right? We proved that we have a set, that almost surely for each number k, we have a set, right, that we obtain via the circle packing, a set of size linear in k. Right? So I can think about it as a connected set containing the origin, so that if I look at the resistance from my center to the outside of the set, this resistance is at least logarithmic. So let's just remind ourselves of that. So in U star, U star rho star, right? So for this statement, I don't even need the new edge resistances. So this is just a statement now about the random walk with unit resistances on this one. So we know, so we proved, and this is where we use all of our machinery, the circle packing theorem, the magic lemma, all of our resistance estimate. We proved that almost surely for any k, right, there exists some set bk, right, such that one bk is linear, yes, but if you close the window there will be no air. Okay, oh, thank you. Right, and that the effective resistance between the root rho star and the outside of the bk and u star minus bk, right, is at least c log k, right? When here these are re that are unit. Let's call them unit. So this is just with respect to the simple random walk, right? So and now we can already see a proof, right? Because so what this means, what this means is that if I look at the simple random walk on this graph and I look at my set k, right? So this was the origin, and this is a ball of radius, some radius in which that told us this was, just to remind you, k to the power 1/3, right? And this is bk. So what I know is that if I take the simple random walk, right, the probability that I go to the outside before returning is of order 1 over log of k. And I also know, so this is one thing that I know. And the second thing that I know is that I never visit a vertex. Right? This is a graph of bounded degree, but that I never visit a vertex that originated in the original graph from a vertex that had degree more than log k. Right? And this is exactly this point. And why is that? Right? And the reason is I used here the what was written here earlier, the commute time identity, right? So I know that this set is polynomial in K, right? It's just a set that is linear in K, right? So the time that it takes me to get from here to the outside, right, is bounded above by some polynomial in K, right? And in this time, I will not see any degrees bigger than log K, right? Because of the exponential tail. So that means that with high probability, I'm walking here on vertices that their original degree in the original unbounded degree graph, all the degrees here were smaller than log of K. Right? So I never walk on these very few vertices that have very high degree. Right? And if I only walk at these logarithmic log in K degree vertices, then what I get, right? Then I can imagine that the vertices of higher degree do not even exist. So I can imagine that in fact, when I look at this fixed set BK, I can imagine that all of my resistances are at most 1 over log K. Right? And if I have a network and the resistance between A and Z is 10, right? Just a unit resistances is 10, and now I multiply all the resistances by the number 1 over 5, right? Then the effective resistance between A and Z is going to be 2, right? It's just linear. If I multiply all the edge resistances by the same number, it drops by that number, right? Because the unit current flow does not change, right? And its energy decreases by exactly that number, right? So what I get, so if you believe all that, what I get is that the effective resistance between rho star and U star minus BK. Now, when I'm adding not in the simple random walk, but when I look at the walk induced by RE, by the new edge resistances, then this is at least a constant. Right? And this holds for any K. Right? So what we discovered here, right, this constant does not depend on K. I can take K to grow, and I get that the resistance between the center and a ball and to infinity is at least a constant, which is not a very impressive thing, right? Because that is true just because the degree of the root is some constant, so it will be at least the resistance to infinity will be at least 1 over the degree. So why have I worked so hard? So I get this for any K. Right? So in particular, the limit over K, but in fact, I get something a little stronger than this, which just suffices to prove recurrence. Not only is let me show you the last bit, right? So before I do this, right? So you have to be convinced indeed that because I have not walked on vertices of high degree, that I can indeed then all of the resistances that I visited cannot be more than 1 over log K. So so I divide by log K, and I get here that this is bigger than some constant. But in fact, the same argument tells you not that just this is true, but also not just looking at the resistance from a vertex rho to infinity or to the outside of a box of radius K, but also when I look at any finite ball around rho. Right, so this radius in the graph distance will be radius m. M is fixed now. Right, so what I get by the same kind of argument is that the resistance from the ball in U star around rho of radius m to U star minus bk, this thing is bigger than c log k minus, so if I know this for rho and I look at a ball of radius m, right, how much do I need to subtract at the worst case scenario? Now I'm looking at, instead of the root vertex, I'm looking at a neighborhood of it, of a small neighborhood of some radius m. Right, so the resistance is going to be smaller than just from the root that is inside, right? Because I have leeway, but I'm claiming that I never lose more than m. Right? And the worst case scenario is indeed when rho is here, right? And outside of it, there is a path of length m. And now the rest of the graph, bk, comes, and this is the outside. And this is the width. So from here to here, it will be m plus this resistance, right? But in fact, it's true. This is the worst case scenario. This is easy to prove because so this is a fact that is true for any network. If you have a network from A to Z, right, and I'm looking at a ball of radius m, then I want to say that the resistance from A to Z is at least the resistance from this boundary of the ball of radius m to Z. Sorry, the other way around. The resistance from the boundary of the ball of radius m to Z is at least the resistance from A to Z minus m. And this is simply because I could take just the best flow from A to the boundary of m, and then attached to it, this flow has energy that is at most m, right? Because the distance is m. The effective resistance between two vertices is always bounded by the distance between them. And attached to it, the flow that ignores this part treats this as one vertex and sends the electric flow to Z. Okay, so this is something that you convince yourself. So not only did we prove a bound like this for rho, right? Just because of the same picture, we prove it for any neighborhood of rho, of fixed radius. So now m is fixed. And now the same argument as before tells us that because we are stationary and we have not walked on vertices that originate in degrees bigger than log k, then we are allowed. So this was in the simple random walk. If I look at the new resistances, I have to divide this part by log k, right? Because in fact, I ignore all the resistances, all the degrees that were higher than log k, because I don't walk on them, right? So they do not affect the resistance. Right? This is a very intuitive statement that needs to be proved, but it really is not very difficult, right? So what we get is that the effective resistance from for any m and any k, think about k much bigger than m, the ball in U star rho m. U star divided by bk in the new edge with the new edge resistances, right? This is bigger than c log k divided by k minus m divided by log k. And now I take k to infinity, right? I take k to infinity. And what I get is that the resistance, right, between any fixed neighborhood of the root vertex, right, B, U star, rho star. So I guess all of these rows should have been rho stars, right? This is the original root. This is the root in U star and not in U. Rho star m to infinity, right? M over log k goes to 0, right? This is bigger than some constant. Right? So I have a graph. Not only the resistance from the root to infinity is at least a constant, but if I look at any ball around it, this is at least a constant. And this event holds almost surely on the choice of U rho. Right? You have U. This is the only randomness that we have. Right? And I claim that this event, if this occurs, then the graph deterministically has to be recurrent. Right? So it's not only that the root has resistance at least a constant to infinity, but also every neighborhood of it. So why does that imply recurrence of the original of the graph? From every, no matter how big the radius in the graph that I'm looking, the resistance is always bounded by some constant that does not depend on the radius, right? So this means if I look at radius 1, just the root, I can find some ball in which the resistance to it is some constant. Now I take this ball, the resistance from the boundary of this ball to infinity is also a constant, so I can find an even bigger radius. So from the small ball to the big ball, it's at least a constant. And then from the new radius, I can find an even larger radius that it's always a constant, right? And then I'm using the series law, right? And add all these constants together, and I get that the graph that we obtain is recurrent. Okay? Are there any questions about this proof? So I thought I would show you some details of this argument actually occurring. But I think I'll skip the details if you don't mind. Any questions about this? So the details are, at least in my opinion, once you've heard the strategy and you agree that everything should work, so there are perhaps some things that you need to convince yourself that indeed I never walk on high degree vertices. This follows from stationarity, but why it doesn't follow almost surely? Right? Because you need to say, you need to have an almost sure statement. Okay, but we're all adults, so you find good bounds on the events and you use Borel-Cantelli in the right way, and this is performed in page 64. Nothing is surprising there. And you also need to say, okay, so you needed to use the commute time identity to say that the time it took you to reach from here to here is polynomial, and the event of seeing polynomial in k, and the event of seeing a large degree, a degree bigger than log k, is exponential in log k, so I can fix the constant in front of the log k to be such that it dominates, right? So that this probability is much smaller than the time that it takes me, right? And I can make it all so small polynomially that all my Borel-Cantelli will work. So almost surely, both on the graph and on the random walk, I never touch a vertex that is of high degree, right? So this is clear that I can do, so this is the one technical bit. And then you also have to convince yourself, okay, so if with high probability I don't walk on these vertices of high degree, is it true that I could just erase them and and my resistance has not grown by too much? Surely this is also true because we have an interpretation of the resistance in terms of probability, right? The probability of hitting here before here. And I know that these, right? I know that these don't change. If I look at the resistances around vertices that are very unlikely to be hit, then these probabilities will not change, whether I erase them or whether I keep them there. So that means that the resistance, if I erase these vertices, cannot change by a lot. Right, so this is also, I control the new resistances just by controlling the random walk this time, right? So it always goes in both directions. So this is also possible to do, and this is also done at page 64. And then this argument at the end is essentially what I showed you. It's just at page 67 of your notes. And the rest of these pages, 2 more pages in these notes, is to deal with all the mumbo-jumbo of choosing the roots in the proper way so that you always get something that all of these choices of roots give you something that is absolutely continuous. So and mutually, so you never lose that. So this is the proof up to the pesky details that the UIPT is recurrent. And in the next 15 minutes, I thought I will entertain you with some exposition to my last class. Are there any questions about this proof? Or about anything of the last 7 lectures? So, yes, please.
I don't see what is the exact place where you use the exponential detail.
Okay, excellent. So this perhaps I did not explain this properly or enough. There are 2 logs that are competing with each other. right? So he asked why did I only with exponential decay? The first log was to use the exponential decay of the degree and the stationary to say I never walk on vertices that their original degree was too high, was bigger than log of k. That's one log, right, that you get from the exponential decay. The other log is this log, right? Where did we get this? This is a completely unrelated log. This we got from the quantitative, this we got via the circle packing. Right? We have a bounded degree circle packing. We're looking at radius r. The resistance from the origin to r is log of r. Right? This had nothing to do with the degree. Right? This was just our circle packing effective resistance techniques of putting annuli after annuli and getting log. So this log, eventually, I'm dividing by, right? Here, when I divide it by log, is the log from the exponential decay. Right? So they all match together, and it's exactly the case. Right? Anything that you give up on one of them, and the proof fails. And indeed, exponential decay is tight in the sense that if you have any other stretched exponential estimate on the degree, there is a counterexample to this theorem. Does that answer your question? Any other questions? Okay, so in the next 15 minutes, I will tell you a little story about a different model, because I promised to tell you, or at least in the beginning, I told you circle packings are good, not just for random walks, but to study other models of probability as well. And this is a convincing pitch that I like to make. So let me try to tell you a story about a little bit about the uniform spanning tree. And tomorrow I will try to complete the story and tell you how you can prove something very nice, or at least I think is nice, about the uniform spanning tree on planar graphs. Using the circle packing theorem, of course. Otherwise, what's the point, right? So the uniform spanning tree so this part of the lectures will be chapter 7 of your notes. I have not written it yet, so in the next lecture you will not have notes. Oh my God! So what is this model? It's just as its name say, but perhaps to confuse you a little bit, I'll add here tree/forest. And it's a very simple, intuitive model that everyone likes. It's very popular in discrete probability. You start with G as a finite connected graph. And you look at the set of all spanning trees of T. So T subset of G, right, is a subgraph. I consider T as a subset of edges of G as a spanning tree. So this is a definition, is a spanning tree if it has no cycles. So it's a tree if it has no cycles and touches every vertex of G. And touches every vertex of G. Okay, so for instance, if your graph is this, right? Just where the vertices are where edges meet. Then a spanning tree could be something like this, right?
It needs to be connected, right?
Oh yes, I forgot to say connected. Has no cycles, touches every vertex.
You could just say it's connected because it already touches every vertex.
Yeah, it already touches every vertex, so it has to be connected. But let's just add connected, even though it follows. Does it follow? No, it does not follow. It does not follow, right? Right. You can have any spanning for, right? Or you can have. It does not follow, right? I can have this graph right? Touches every vertex, but is not connected, right? So it also needed to be connected.
Yeah, but the way you define a subgraph, it always touches every vertex.
Well, here, this subgraph touches every vertex.
Yeah, but
It has no cycles, and it is not connected.
I mean, the vertex set of a subgraph is always the full vertex set. So you
Touches every vertex means that for every vertex, there is an edge that touches it. Okay, so it doesn't, and that's what it means, right? So here's an example that you really need the word connected. Okay, so are we all, we're all, yes, question?
But at the top we said it could be a part.
Okay. This was just the title, it's not a mathematical statement. Okay, okay, so the first thing that we may ask, so we have any finite graph, you know, part of Z2, the line, you know, if, you know, any graph that you want. You look at the set of all spanning trees and you realize to yourself that this is just a subset of edges, so it's a finite set, right? The number of spanning trees is a finite set, and we would like to draw one at random, right? Does anybody know what is the cardinality of this set? There's a theorem, right? Who is the author of this theorem? Sorry? So Cayley is, right, so we all know, so even before this, in fact it was after, there's when your graph is a complete graph, how many spanning trees do we have? This is just because every tree is the same, so when G is Kn, right, the number of spanning trees is n to the power n minus 2. And this is indeed Cayley's theorem. But what if your graph is not the complete graph?
There's a determinant somewhere.
It's a determinant of something, right? And who is the name? It's a Kirchhoff, who is Balin's dear friend from 1850. Yes. So he indeed provided a formula. You look at the adjacency matrix of the graph. This is you can think to yourself that this matrix is always singular, right? It has zero eigenvalue, but because it's a connected graph. If you take any minor of it, then it will actually be invertible. You compute the determinant, not exactly perhaps of the Laplacian matrix. You take a minor, any minor that you choose gives you the same number, and magically this number turns out to be the number of spanning trees for some reason. But Kirchhoff, in fact, proved something that is, and we know, and this is sometimes shown in combinatorics classes, but in fact his original paper contained the much more, at least in my mind, and I hope that after 2 weeks here, this will be in your mind as well, provided a very nice formula or statement about not exactly the number of spanning trees, but about the probability that a particular edge is in the spanning tree, right? So let tau be, or perhaps let's just keep it t, be a uniformly chosen spanning tree. Yes, and Kirchhoff proved that if for any g and any xy an edge in this graph, he gave a formula for the probability that this edge is in T. And E is a fixed edge of G. All right, and let us try and guess that formula without proving anything. So if your graph is, if this is the edge xy, and your graph is drawn like this, what is the probability that xy is in the uniform spanning tree? 1, right? Because without this edge, the graph is disconnected, and the tree has to be connected, right? What is going to be? Let's look at this graph. I have 4 vertices right? And this is the edge xy. What is the probability that xy is in the uniform spanning tree? Sorry? 3/4. Why?
You choose one edge and you get it.
Right, there are 4 spanning trees here. Right? The minute I erase one edge, there are 4 spanning trees. And if I did not erase this edge, then it's in the spanning tree. So here the probability is 3/4. Right? Here, the probability when here I have whatever it is, the probability is 1. Let's even draw it in. 1, 3/4. Let's take even a simpler graph. What will be the probability here? And this is the edge xy. 2/3, right? By the same. And what will be the probability here if I just have one graph with a double edge? So what is the formula? Any guesses?
So something to do with the cycles, right?
Nice, nice. The formula is that this is the effective resistance in your graph between x and y. Right? And that, you have to admit, is pretty awesome. Right? And you can see it here. Here we use the parallel law. Right? And this will have resistance 3, and this will have resistance 1. So 1 plus 1/3 is 4/3, and this is the conductance, right? So the resistance is 3/4. And we also see that, in particular, the resistance is non-negative, so this is always a number bigger than 0. Why is what's written here is always smaller than 1, or equal to 1? We've seen that resistances could be very large, right? But sorry? They're a distance 1. There is an edge, right? So I always have a flow that goes right on that edge that has energy 1. So, and this is an upper bound on on the infimum of the flow. So the energy is always, at most 1 of the best flow. So this resistance can be no bigger than 1, right? So this is a pretty awesome thing that I will prove to you tomorrow. And from this you can get, so now you can answer the question. For instance, calculate to yourself in this graph, what is the if this is xy, what is the probability that it exists, that it's in the uniform spanning tree? Oh, it's 4/27. Then can't you tell? Well, of course, you know how to do it now, because you just use the parallel law here, the parallel law here, you get a cycle, you get 4/27, but the honest truth is I just made up this number now, so perhaps it's a different number, but clearly you have a way to compute this in most cases. Why is this nice, and why did I write forests, right? Because now I want to define the uniform spanning tree of an infinite graph. Okay, so this is, now we're more afraid. So how will we define it? Who has a natural inclination? What will you do? Yes, if you're doing this gesture, you are correct. I have an infinite graph, for instance, Z2. I will take larger and larger balls in this graph, larger and larger graphs, and draw the uniform spanning tree on each of them. Consider it as a measure on subset of the edges. And I hope that these measures converge. Right? And indeed, these measures converge. And immediately you see, just from this fact, that the probability that an edge is in the tree converges, right? Because you have resistances between xy in a graph that becomes bigger and bigger. So we have Riley's monotonicity. This resistance only decays, right? So the one-dimensional marginal of this limit of measures exists and is given by the effective resistance on the infinite graph. Let's observe, just before we finish, assume we have a limit. Let's observe some basic property of such a limit. Right? So if I look at a vertex in my infinite graph, Right? I have an infinite graph drawn. It doesn't have to be planar. I have an infinite graph drawn on this whiteboard, and there is a big part of it. So I know that in each finite graph, big finite graph, there has to be an edge of the tree touching it. Right? So that means that in the limit, every vertex will be touched. Right? And also, I can look at any fixed cycle in my graph. Right? This is a cycle of length 4. Fixed cycle in my graph. Right? I have countably many such cycles. And I claim that in any such cycle, right, eventually, right, it will be exhausted by the finite graph. So I cannot have that all of these edges are present. Right? So one of these edges will not exist. So that means that in the limit will be a subgraph in which a subgraph of edges in which that has no cycles and every vertex is touched. Does it imply that it is connected? I guess not, right? So if you want to say, these two vertices are on the same, are in the same cluster, so of course it's true for any big chunk, right? Here I'll have a thing, but this path could go farther and farther away as you increase the exhaustion, and in the limit they will not be connected. Right? Can this really happen? So here's a theorem of Robin Pimentel, really, whatever. In ZD, the limit of the uniform spanning tree, right, as you take growing and growing balls, is connected almost surely if and only if D is 1, 2, 3, 4. For dimension 5 and above, the limiting object that you get is not connected, and in fact, it has infinitely many infinite trees. What we will prove is that so in particular, in D equals 2 and D equals 1, it is connected. What we will prove is that if G is planar, with perhaps a slight star here for exactly what we mean, but for all the planar examples that we know of, the limit of this UST is connected almost surely. Okay, this is what I will show you the proof of tomorrow. This is joint work by myself and Tom Hutchcroft. So thank you very much.